The periodic table of the elements is perhaps one of the greatest crowning achievements for scientists in all of science. It represents our ability to look at the universe that God has created for us and to recognize patterns and consistency in that universe, to identify the very things that the universe is made up of. You see, at its most basic, the periodic table of elements is a list of all of the possible ingredients that can make up the universe. And scientists have worked painstakingly over the years to identify those different ingredients. But the periodic table is so much more than just that. It also recognizes that there are relationships among the elements, ways that elements are similar to other elements but different from other elements, and we can start to understand the reasons why some elements have similar properties and different properties from other elements. That's what we're going to begin to explore today, is how the periodic table has structure and organization in the way the elements on the periodic table are arranged. In this lesson, we're going to explore the structure of the periodic table of elements. And we're going to begin looking at that structure the same way that the scientists who began looking and understanding that structure started. They looked at some of the known elements and their properties. Now, when scientists began this work back in the 1800s, there were really only a handful of known elements. Today we know about 120 elements on the periodic table, but back when this work started with scientists like Dmitri Mendeleev, the father of the periodic table, there were really only about 60 known elements. Here I have a sampling of some of the known elements from Mendeleev's time, but some other elements that he wouldn't have known about. I've chosen these elements because it's going to help you to understand the way that the periodic table is structured, to look at the properties of some of these elements. Now, this is a little unrealistic because scientists at the time of Mendeleev wouldn't have recognized that atoms are made up of protons, neutrons, and electrons, even though you can see that I've clearly pictured all three of those parts here. So I'm going to show you what scientists at the time of Mendeleev would have pictured when they thought of atoms. They thought of them as simple, uniform spheres of different sizes, and they considered that the size somehow probably gave the atoms their different properties. These numbers represent the masses of the different kinds of atoms, and many of these masses were actually known at the time that Mendeleev was working on describing how these elements were related to each other. What I'm going to do next is remove two elements that are particularly troublesome to identify where on the periodic table they go. These two elements weren't actually known at the time of Mendeleev anyway, and those are the two way at the top, helium and hydrogen. We're going to get rid of those for right now. I'm going to take the rest of these elements and I'm going to line them up. Here you see I've lined up the elements that we're considering in order from smallest mass on the left to largest mass on the right. Let's take a moment to consider the properties of each of these different kinds of atoms. Lithium, way on the left, is a highly reactive metal. Beryllium is somewhat less reactive but still a metal. Boron is not really a metal anymore. It's a substance known as a metalloid, which means it's sort of like a metal, but sort of like a nonmetal. Carbon is decidedly nonmetal, and it's not very reactive. Nitrogen is more reactive and a nonmetal. Oxygen is even more reactive and a nonmetal. Fluorine is even more reactive. In fact, we'd say highly reactive. And then neon, not reactive at all. Next, we have sodium, which seems to start repeating that cycle of properties that I just went through. It's a highly reactive metal. Magnesium, a metal, but not as highly reactive. Then we have a fairly unreactive metal, a metalloid, a nonmetal that's kind of reactive, a nonmetal that's more reactive, a nonmetal that's extremely reactive, and then a substance that's not reactive at all. Did you catch that there's a flow in the properties of these different kinds of elements as you go from smallest mass to largest mass? It starts off as a metal that's very reactive, becomes less reactive, changes to nonmetals that aren't very reactive, then gets more and more reactive as nonmetals, and then finally ends with a completely unreactive nonmetal. And then the cycle repeats itself. Mendeleev recognized that there seemed to be a cycle in the properties of the elements. But what made Mendeleev different from other scientists is he decided to line the elements up according to these properties. And because he did that, because of that one step forward, we have the modern periodic table. So he started lining elements up according to their properties, and then when he recognized that the properties started to repeat themselves, he took the next batch of elements and lined them up underneath the elements that they were similar to. And that's how the periodic table was born. Let's bring back hydrogen and helium and consider where they fit into this arrangement. Hydrogen is an extremely highly reactive substance, but the problem is instead of being a metal like the elements start on the periodic table, it's a nonmetal. Helium is a completely unreactive nonmetal. Over the years, scientists have realized that hydrogen really fits best above all of the highly reactive metals, even though it's a nonmetal. And helium, just like all of the other completely unreactive nonmetals, fits best in that last column on the periodic table. So because these two are on opposite sides of the periodic table, and because hydrogen is a nonmetal that fits in a category of metals, they're a little bit harder to place, but scientists understand why these two elements are the way that they are and why they belong in the periodic table where they do. These two elements are also the reason why the periodic table has a spot that sticks up on either end of it. Now that Mendeleev had laid out his periodic table of the elements, he can start grouping the elements by their properties. For example, the first column of the periodic table is made of highly reactive metals, except for hydrogen, which is that one weirdo that is a nonmetal but behaves like the highly reactive metals. Then a group of fairly reactive metals. And then metals that are not very reactive at all. Notice that reactivity gets less as you go across the periodic table. Then a group of elements that behave sort of like metals and sort of like nonmetals. And when you cross that line of metalloids, you have all nonmetals, some that are somewhat reactive, some that are fairly reactive. Again, we're getting more and more reactive toward the end. The extremely reactive group of nonmetals. And then finally, a group of completely unreactive nonmetals. Now, scientists have spent years and years figuring out why the elements fall into these different categories. In this unit, we're going to be exploring what it is about different elements that cause them to be highly reactive or unreactive or shiny or dull. Those are the sorts of things we're going to be exploring in this unit. Now that we figured out that there's regions of similarities on the periodic table, let's consider all of the things that the periodic table of elements shows us. It organizes the elements, so it really shows us three things. The first thing that it shows us is how the atomic masses of elements change as we move across and down the periodic table. You can be pretty sure that elements higher up on the periodic table are less massive than elements that are farther down. Same from left to right. Elements on the left are usually less massive than elements farther to the right. What that means is that as you get farther down the periodic table, the elements get bigger and bigger and bigger because they have more protons and neutrons. And in fact, that number of protons is extremely important because that's the second thing the periodic table of elements shows us. It shows us how many protons each different type of atom has. Remember, the number of protons determines the properties of each element on the periodic table. So it's very important that we know how many protons each atom has. The number of protons, by the way, is always listed at the top of the element square. And for each element on the periodic table, it always counts up by one more proton than the previous element. If I were to peel away that outer layer of the atom so you can peer inside, you can see that each of these atoms on my periodic table has one proton more than the previous atom had. And then finally, the periodic table shows us the properties of atoms. The way that atoms are lined up on the periodic table, we know that atoms that are nearby, and especially in the same columns, have the same basic properties as one another. They're related to one another in a very important way that we'll be learning about later on in this unit.